as I go along, because I don't need to get through all this material. I just, I just hope that you would understand what I do get through. So feel free to ask questions. So I've been actually thinking about this for a little while, trying to figure out if you can think of a monsoon. There's lots of descriptions of monsoons, but the question is there a common physics or is there different physics? And I think you can actually lump them into 3 different physical processes. And I'll argue that here. And then I'm kind of throwing that out there. I'm going to write a review paper on all of monsoon stuff right now. And I'm kind of throwing this out there as a way of organizing the material, that there are actually 3 different physical types. If you look at the dynamics behind the monsoons of the world, there's 3 different, I think, very different types of monsoons. Okay, so how do I move this forward?
I think that's just this keyboard.
Okay, yeah. Put it right here.
I think that this is the most that we can. Oops, there we go.
That's good. That's good. Yeah.
That's there. So the arrows.
Yep. Yeah, good. So there's 2 ways traditionally to define a monsoon. One is the seasonal changes in winds. Actually, that's the first definition that comes back from the Arabs in like about 900 AD. And that's simply because why the monsoons were important then, the winds were important because it was trading. It wasn't about the rainfall, it was about the winds, so how are you going to run your ships, your sailing ships. So the first definition was winds. And now we actually think of it rainfall changes, seasonal rainfall changes, and they're pretty similar actually. So if you define a criteria based on the winds have to be pretty strong in 2 different seasons and change directions. So whatever the dominant component is, east-west or north-south, if you say that the winds have to be at least 4 meters per second in those 2 seasons and have to change directions, then you find everything in red is defined as a monsoon region, where the winds change really dramatically. And it picks up some of the traditional monsoons, like you can see here all in Australasia, this region here, there's monsoon. East Africa, there's monsoon. You might say there's a monsoon in Africa. You wouldn't say there was a monsoon based on this definition in South America, but I think everyone would call it monsoons, right? So here's one place where the traditional definition breaks down. And actually there's, I guess you'd say there's a monsoon in Seattle where I live, because the winds come from the south in the wintertime and they come from the north in the summertime. Okay.
There's also a monsoon in southern Chile.
And there's the southern, yeah, right here. Yeah.
Now it makes sense.
Yeah, now it all makes sense, yeah. Okay, so that's the traditional definition. You'd say Africa for sure, North and South Africa, the winds change here, the winds change here. East Africa, all of this region here is the kind of dominant region under that definition. Okay. If you base it instead on changes in precipitation, this is places where in DJF, summer, JJA, winter, where the precipitation rains on average more than 7 millimeters per day. And I've just contoured that 7 millimeter contour. So you can see northern hemisphere summer, it's raining up here. Southern hemisphere summer, it's raining down here. So there's a clear change in where the heavy rains are happening in the Australasian monsoon. Even here in Africa, summertime, heavy rain up here, relatively heavy, and summertime, rain down here. Summertime rain here, summertime rain here. So you cross the equator, right? And even in the ITCZs, you could argue that there's a monsoon. And I don't know, this is, so you can see that the rainfall in northern hemisphere summer is here, the rainfall in northern hemisphere winter is down here. So there's a migration north-south of the ocean rain bands that you could call monsoon. Not so much in the Pacific, but you can definitely see north-south movement in the Pacific. Okay, so there's like places you might just label monsoons based on arbitrary definitions of wind or rain. Okay, and you could even classify the Atlantic and Pacific intertropical convergence zones. These features here is monsoons. Okay. Under the wind definition, you can include the southeast U.S. The winds change here directions in the southeast U.S., but the precipitation is uniform all year round in the southeast U.S. Okay, so let's. What I'm going to argue is that there's there's three dynamical monsoons, very different. One is the classic monsoon, which I'll only set one slide on. One is a maritime monsoon, which actually involves atmosphere-ocean interaction and doesn't involve anything to do about land. And the third one is these ITCZs that migrate back and forth. And I think the physics of these three classes of monsoons are really different. Okay, so the classic monsoon, this is actually out of the book that you're using, I guess. Okay. Okay. It's basically like in the summertime, the land heats up, the air expands, it creates a high pressure aloft, it pushes the air offshore, it's replaced by air coming in onshore, that air's got moisture in it because it's coming from the ocean, and in the rising moist air, it rains. And so you get this kind of positive feedback here, and that's the classic monsoon that we're all taught in the beginning meteorology classes. And the winter monsoon is the opposite. The land cools a lot compared to the ocean because of the difference in the heat capacities, which means that the rising branch is offshore. This is kind of like a glorified sea breeze, but lasting all summer long. Okay, so that's the classic monsoon definition. Okay, so, and then you can think of then a completely different type of monsoon, which is atmosphere-ocean interaction, where there's no land involved at all. Okay, and that goes, here's an illustration of this. It's my favorite illustration because it's really simple. This is a water world. There's no land on this world. It's coupled to a motionless ocean, so and the ocean is there's going to be two different experiments here with different depth. And the atmosphere is just interacting with the ocean in this thing. There's no land. And what they did is, these people did, is they said, okay, we're going through the calendar year from January to July to December. And what they're plotting here is in the Indian Ocean sector, just the average rainfall in a zonal band across the Indian Ocean. So in southern hemisphere summer, the rainfall maximum is south of the equator here. And as you go into northern hemisphere summer, the rainfall maximum this is observation, switches to the northern hemisphere. Pretty far north, actually. The maximum here is at 20 degrees latitude. And then it comes back down again. And they were arguing in this paper that this switch here is really rapid as you move from the equator, off the equator to 20 degrees north. And then they said, let's just take an atmosphere model, couple it to an ocean model, and a slab ocean model. Let's make the ocean model 1 meter deep. And what happens is, as the sun goes like into the northern hemisphere summer, the water heats up, because it's only 1 meter deep, it heats up really fast. And it heats up enough that basically draws the convection from the equator all the way off the equator to the northern hemisphere. So they can see this flopping back and forth with the rainfall is happily living up here at 20 degrees north in summertime, and then it rapidly switches down here and lives down here 20 degrees south in wintertime. You could say that's a monsoon. Really big seasonal changes in rainfall, huge seasonal changes in wind, and abrupt changes. And if you do this with a 100-meter depth ocean, you don't get these changes simply because the changes in the sea surface temperature are very small relative to the 1 meter ocean. And it's very difficult to get enough energy in the surface air far off the equator to actually pull the rainfall from the equator to the higher latitudes, to 20 degrees north. And that's they argued this based on some literature and some stuff that they had done. So they showed that if you look at the wind at 15 degrees north, so you're just north of the equator right here or so, and you just look at the wind as you go through the calendar year, in the observations, which is green here, it goes from easterly to really strong westerly as the monsoon kicks in. Let's see, I could draw a picture of this here. So if this is, let's see.
There's an eraser in?
Yep.
This looks like problem 1 in control 1. Yeah, something like that.
So what they're saying is that normally if you look at sea surface temperature, you go around the equator, it's highest at the equator, so this would be the equator, this would be sea surface temperature. This would be, say, 20 degrees south and 20 degrees north. And this is the annual average, but then you have the summertime northern hemisphere, it might more look like this, because just of the energy from the excess sun in summer. And the wind, and then it'd be like this. And then in the southern hemisphere summertime, it would look like more like this. So it's just going back and forth. And they're saying if the ocean's shallow enough that this temperature here can get high enough that the rainfall will shift from the equator, off the equator to here. Okay, and it is true that the amount of ocean interacting with the atmosphere in the Bay of Bengal is only 15 meters. The mixed layer is 15 meters deep, which is really shallow. So the sea surface temperature heats up really fast in the Bay of Bengal as you go into summer. And it cools down really fast as you go into winter. Okay, and they argued another thing here. I might as well just draw this. When the rainfall is sort of maximum right here near the equator, you end up with like 2 Hadley circulations. And there's a lot of literature on these circulations now, these Hadley circulations, what drives those Hadley circulations. We're all taught that they're driven by the amount of heating here. That turns out not to be true. It turns out that they're mostly driven by eddy momentum fluxes up here, which is a longer story that I don't want to get into. But if you look at the strength of the Hadley cell and the strength of convection, it's actually driven by the mid-latitude eddies, not by the heating itself. And it's very difficult, and since the strength of this is controlled by the mid-latitude momentum fluxes up here, it's really hard to move this off the equator. And what they argued is the only way to do it is if you make this temperature, it's not so much the temperature here, that if you make the amount of energy off the equator enough, this will switch the beam from here to here, and because of a whole bunch of feedbacks, and if it switches so the convection's out here, you'll get one big Hadley cell that actually crosses the equator. And in this, because of the dynamics, the momentum fluxes no longer matter to this thing. And they argue that that switch from here to here is really rapid. And once you can pull it off, they say that you can reform this new circulation, this off-equatorial monsoon, really fast, abruptly. Okay, so that's their argument, and I think it's true. The question is, how true is it in nature? It's definitely true in an aquaprime model, that's what happens. And here's the references. Okay, it supports abrupt transitions. I can't remember where this movie is, so let's just, have you shown a movie of like, just clouds moving?
We see it from time to time, but it's always good to see.
Yeah, actually,
Just
it's on my
clouds.
laptop. It's on my laptop, not on the.
Oh, I see.
Yeah,
But we have seen.
Okay, good. Okay, good. So, that's kind of the view of the Indian monsoon now. If you talk to people working on the monsoon, kind of the cutting edge in the States, that's pretty much the view everyone has of the Indian monsoon. That actually it's not about India. It's not about heating the land. It's about heating the ocean. And the ocean is building up moist static energy. In fact, if you take a climate model and you sink India, so you just replace India with water, the monsoon gets stronger. And that's not a surprise because you have more energy around. So this idea that the land heats up, India heats up, draws the air in, certainly is not what's going on today in India. Okay, so we'll talk about India more in a second. But these ITCZs, these banded structures across the Pacific and across the Atlantic, there's 2 ways you can look at these features. One is in a zonally average sense, where you're just looking at the stability of the flow in a zonal average sense. So if I think about this now, and I think here's my equator, and I'm saying northern hemisphere, or let's say southern hemisphere summer, and it's summer, I'm going to have warmer water over here and colder water over here. It's going to want to pull the ITCZ off the equator. But what that does is it creates low-level shears down here near the surface, which are unstable. And so in a 2-dimensional sense, if you start trying to move this convection off the equator, you end up with instabilities in the flow that really quickly stabilize it. And this has been known for a long time. So in a 2-dimensional view, you end up with these symmetric instabilities that actually make it so that the convection, the rainfall, is going to want to come back to the equator. And it's really hard to get it away from the equator. So that's the 2D view. In the 3D view, you don't need these instabilities. It turns out that there's large-scale synoptic waves in the atmosphere that organize the convection, and these waves propagate westward, really, really close. And this is really obvious. And here, I think I have a schematic of 2 of these. In the Pacific Ocean, so this is what these guys did is they said, let's go out near the date line, and we're going to composite basically outgoing long-wave radiation, a proxy for rainfall, with the low-level winds and the low-level pressure differences. And they're saying, if I composite against the meridional wind on the equator at time 0. I get strongest winds northward, because that's what I'm doing. I'm compositing about the wind. And the convection is out here. And then if I do it, if I say, what were the flow fields like 2 days before that? The answer is, it looks like this, and the convection's over here. 2 days after this, it's over here. So if you can see, if you trace this rainfall, it's moving westward, right? And I'll just connect those dots here. So if you do this, it's moving westward. So this is a synoptic disturbance. It's got a scale of about 1,500 kilometers. It's slowly moving westward. And it's got a preferred latitude band, which is about 7 degrees latitude. Okay? So, and it moves westward at about 7 meters per second. And if you just sum up these things over the course of a season, you end up with an ITCZ. So a lot of the rainfall in the ITCZ in the Pacific is this beast, which is called a mixed Rossby gravity wave. Or it's people in the synoptic community will call it easterly waves, but it's a mixed Rossby gravity wave, which is a fundamental mode of the equatorial oceans, atmospheres. Okay, in the Atlantic, you get the same thing. You get a disturbance, a convective disturbance start here in equatorial Africa. 2 days later, it moves here to the coast, and 2 days later, here it's in the central Atlantic. And if you average all these things over the course of a summer, you find out there's a band of rainfall that happens right here, which is the Atlantic ITCC. So here are the two ocean rainfall bands that move north and south with the seasonal cycle, but they're really comprised of these synoptic activities. It's not like if you look at a satellite map, you see a line of convection here. You don't. You see a blob here, you see a blob here. And if you watch movies of them, you see these blobs moving east to west.
We have a movie of that somewhere
Yeah.
in a folder.
Yeah, or maybe
there.
we could show it up,
Yes.
yeah, like at the end, because it's really striking. And if you look at the Indian monsoon, you do not see this at all. You can see nothing like this. So only over the Atlantic Ocean and the Pacific Ocean, you see these synoptic features propagating from east to west along the same latitude band. And that latitude band shifts seasonally as you go into northern hemisphere summer. It shifts northwards. You go to northern hemisphere winter, it shifts southward. Okay. So there's the propagation for this one. It's 8 meters per second to the west. Okay. Oh, what's this about? I don't know. That's not in my slides. This might be. Oh yeah. Oh shoot. There's a figure that's supposed to be here. This is a problem with the Mac. Okay. So let me describe to you what this figure looks like. This is some text from this paper that was written in 1990. If you look in the Indian Ocean, you don't see these synoptic disturbances moving from east to west in the Indian Ocean. What you see synoptic disturbances moving from south to north into the Bay of Bengal. I can draw you what the picture looks like. What happens is, if this is India, and here's like Southeast Asia, and you go over here to like Africa, right? Here's the equator. Is that okay with everyone? You guys oriented? Good?
Yes.
What you see is you see like bands of convection here, and the bands are oriented east to west, but they're not propagating from east to west like you see in the Atlantic and Pacific. They actually propagate northward. And what will happen is this band will propagate maybe to here, and then another one will form down here, and the next time it will propagate to here. And then another one will form down here and will propagate to here. And as you go through from June, beginning of June to the end of June, each one of these bands propagates farther and farther to the north. So you get the impression that the monsoon is just slowly marching up here, but it's not marching up as a one band that slowly goes up here and that's the end. It's actually bands that kind of keep on coming up, and each band goes a little bit farther to the north. Those are the synoptic activities you see in the Indian Ocean. That's very different from the Pacific and the Atlantic. Okay? And like I said, India is irrelevant here. You can flatten India and you get the same answer. Okay, so it doesn't have anything to do with India. It's just these bands that are propagating north. Why do they propagate north? It's because, especially in the Bay of Bengal, the mixed layer is really deep, and as I go into northern hemisphere summer, the water here heats up a lot, and so most of the maximum energy is actually up here in the northern Bay of Bengal. And as the summer increases, that energy becomes stronger and stronger and stronger up here, so the synoptic disturbances just keep on moving farther north. Okay, so that's what this picture would have shown you with cloud bands, but it's not there, okay. So if you summarize this now, you can really collect all the world's monsoons into 3 different dynamical regimes. And I'm going to call the maritime monsoons this thing in the Indian Ocean. And I'm going to call, so there's the typical land monsoon we talk about, where the land heats up, draws the air in. That's not on this slide. Okay? Those exist. There's not very many of them. You can maybe make the case for equatorial Africa, but even then there's not many. Okay. And you can make the case for South America too, that works in South America. It's not entirely the answer, but it's a good part of it. But these are the things, maritime monsoon. So this is just the convection moving up into this region and then back down into this region. Okay, and then you have the maritime ITCZs, which are the Atlantic and the Pacific, where you have these very organized east to west propagating synoptic disturbances along a band. And the physics behind these two things is really different. So here the Indian monsoon, the example of the maritime monsoon, and the Central and Eastern Pacific ITCZs would be an example of these maritime ITCZs. Where do you find them? ITCZs are found within 15 degrees of the equator. The maritime monsoon, the Indian monsoon, is found north of 15 degrees. It's found in the kind of deep subtropics. I didn't go through all the physics, but if you look at what sets the maximum position of the convection, of where the rain is happening, for the maritime monsoon, it's the location of the maximum boundary layer moist static energy. Moist static energy, I don't know if you've gone into this, but it's just the total energy in the air. So it's the gravitational energy. Of course, at the surface, you're at 0, so there's no gravitational energy you could extract. But there's sensible energy associated with the sensible heat, and there's energy associated with the latent heating. If you can condense the vapor, you get a lot of energy out of it. So where that's a maximum turns out to be roughly where the maximum rainfall is, which and I'll show you a picture of this, in the Indian monsoon, the maximum is actually in the Bay of Bengal. It's not over the land, which is why the monsoon is not a land-atmosphere interaction in the Indian Ocean, because the maximum moist static energy is over the water, it's not over the land. So even though India is hot, it's 40 degrees, 42 degrees, 44 degrees Celsius before the monsoon kicks in, where the air is that has the most energy is over the water, where it's only 32 degrees. And that's because of the vapor. The vapor is really potent in terms of giving the air energy. Maritime ITCZs is either, depending on how you all look at this, in a two-dimensional sense, it would be determined by the Laplacian of the moist static energy. In a three-dimensional sense, it's just organized by synoptic waves in the tropics. And those have a scale that's determined by the rotation rate of the planet, the gross greenhouse gas concentration of the atmosphere. So they're kind of, the location of that rainfall, it wants to be near the maximum moist static energy, but it's strongly controlled by the dynamics. Okay. Precipitation intensity, the intensity of convection. Once you've located it, what sets the intensity? In these maritime monsoons, the Indian monsoons, it's really just how much moist static energy you have at the surface. The more moist static energy you have, the more convection you have. In the maritime ITZZs, it's interesting. These are kind of the expressions. Remember, we do the Hadley circulation here. Well, the convection is not lined up on the equator. It's lined up at 7 degrees north or 7 degrees south, and it is these synoptic waves. But that's an expression of the Hadley circulation. So what controls the strength of the convection in these ITCZs actually is, to some extent, how much energy is at the surface, but to a large extent is how much are you pumping the Hadley circulations. And that's done by the eddy momentum transports aloft. So actually the mid-latitudes, storms, control a lot of what's going on with how much upward motion you have in the tropics. In these maritime ITCZs. It's controlled, in fact, you can show this, we did show this in electroclimate models. The strength of the convection is controlled in the Pacific and the Atlantic, not by the moist static energy primarily. It's controlled by the upper level eddy momentum transports. So the physics is, the point here, I mean, there's like a whole month of background equations to actually understand that, but the point is that there are two different sets of physics going on that we understand that controls this. Okay. The strength of hazard circulation in these maritime ITCs are controlled by eddy momentum transports. In the off-equatorial case, like in the India case, we have upward motion here 20 degrees north. It's controlled by the amount of moist static energy you have, the amount of diabatic heating you have associated with your convection. And to some extent by eddy momentum transports aloft, but that's secondary. Okay, so those are the two different types of ocean monsoons. And then you have the land atmosphere monsoon on top of it. So those are the three types. Now let me show you some, and under this type here, you can even explain why monsoons might be abrupt, although the Indians will tell you that it's not abrupt. What they'll tell you is that it's these bands that are slowly moving up here, and each one moves farther to the north. There's nothing abrupt about it, unless you happen to live at one place in space. And then this band comes up here, and then the band comes up here, and the band comes up here, and all the time you're saying dry, 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 dry. And then when finally one band gets to here, you say, whoa, it's raining. It's abrupt onset, but there's nothing abrupt about it. You just happen to have a feature that's slowly moving north and eventually gets to your place in space, and it looks abrupt. Yeah.
So is it just the increase in moist static energy, or is it the preconditioning of the upper troposphere by water vapor of the previous bands?
That's a great question, and that's a great question. That's a good research question. I don't think anyone knows about this. Yeah, yeah, I don't think it's known, but it's a great question. I'm trying to think through how to actually answer that question.
Maybe
Yeah.
both.
Yeah, that's a great question. I'm trying to think how you discern that question, like, experimentally, because it is an important question. It is kind of fascinating. The state of affairs right now is fascinating. So this view of the Indian Ocean monsoon is kind of an atmosphere-ocean thing and not a land thing. It's something that's evolved maybe in the last 10 years. I think, the kind of basic physics was starting to be put down like in maybe 2006, 2007, and the pieces all kind of came together. And it's a community on the cutting edge that all says, yeah, this is it. It makes so much sense. It makes sense dynamically. It's consistent with the synoptic picture, and yet, even in the atmospheric science community, I'm sure that 95% of the people still think the land heats up and draws the air in. That's clearly not what's going on in India. Okay.
But, and the difference between ultimately, the difference is because of the depth of the ocean mix layer?
Yeah.
What makes different Central Pacific with the
That's great.
Indian?
That's great. It's because of the depth of the mix
Isn't
layer.
it?
It's really shallow.
Okay,
Yeah, it's
this is
really
what
shallow.
You show in
Yeah.
the first picture
Yeah.
with the 100 meters or the 1 meter.
If you look at the mixed layer depth actively involved in the seasonal cycle in the Atlantic Oceans and the Pacific, so it's on the order of 50 to 100 meters, and so
Okay.
that the amount of
100.
moist static energy you can get built up way off the equator is really limited, just because it's so deep
Right.
that the temperature changes are small.
And
But-
you said that in this Indian Ocean is much shallower.
It's much shallower, and the reason why it's shallower is because of runoff from the Himalaya. It all runs off into the Gulf, so it's incredibly fresh water, and it stabilizes the mixed layer. And all through the Bay of Bengal, the mixed layer is only 15 meters deep.
Okay.
I think it's the only open ocean place
So
on
at
the
the end
planet.
is the Himalayas, the one
Yeah,
that
it's-
control ultimately.
Yeah, it's really cool. When I was in India last week, we were talking about this. It's like, okay, if you lose it, you're never going to lose the runoff, because it's once the monsoon comes up there, and most of the runoff coming off the Himalaya is the rain from that monsoon season. It's not snow melt. I mean, there is some snow melt, but you're always replenishing it. And you're going to lose the glaciers, but you always have that fresh water that's coming back into that region. Right? But it would be curious to see if you took a climate model and you artificially made that mixed layer deep, would you get a monsoon up into India? Probably not.
With a maritime ITCC.
Yeah, exactly. Okay, good. So here we go. Let's see. So let me. Here's like my summary cartoon. If you looked at a map of the planet, this is actually a map of surface AE. We can see surface energy, and the maximum surface energy is here in the Atlantic across this band here, about 7 degrees or so. Here, there's maximum moist static energy. Here, there's moist static max, and this is January. And in July, it's pretty similar, although it shifts in the maximum moist static energy. July is up in this region. So let me show you. That's where the rainfall bands are in January. and this is where they are in July. So if I go from here to here, the maximum rainfall is right there. Okay? And I think everything's familiar on this map. But now let me classify these as what type of monsoon. So here are the ITCZs, these things that are actually just the synoptic waves propagating from east to west, and you see them pretty much all at the same latitude around the planet. Then you have a land monsoon, which you can definitely classify South Africa as a land monsoon. South Africa is heating up and it's drawing moisture in. But it's also connected to the fact that moisture wants to be down here anyway. And there's an open question here. I just don't know the synoptic answer here, but I assume this is an ITCZ. But I've actually never studied it. But it'd be kind of curious to see if this is just also east to west propagating features here. I mean, that's knowable. I just don't know. I just don't personally know the answer. If you look in July, you still see the ITCZs, and then you see kind of a land monsoon. You can make the argument that North Africa heats up and is drawing the air in, but then really quickly you end up with instabilities that shed synoptic waves. Okay, so it's kind of a combination that the land monsoon generates synoptic waves that propagate then from east to west and forming the ITCZs. And then you have, let's see, then you have your marine monsoons, which is the Indian monsoon. And then you have other monsoons. So here's one that's kind of complicated. It has to do with the fact that you're heating this region here, but it's also important that you have a rocky mountain here to channel the moisture from the Gulf of Mexico up in this region. And here, this monsoon is mostly about the topography of India, of the Himalaya and Mongolia, blocking the flow of the westerlies here, and kind of splitting it, and it's converging on the backside, and it causes an acceleration here, and it causes moisture to be swept into a frontal band, which is called the Mayu band. So actually, this isn't a monsoon at all. This is just basically the flow interacting with topography, concentrating where moisture is being swept in, and it's raining. And of course, once it starts raining, you're releasing latent heat, and that is a positive feedback. Okay, so that's a pretty different process. So that's the Mayu is an orographic rainfall feature where diabatic heating associated with the condensation contributes to it. And this is a more complicated combination of diabatic heating associated with latent heat release and the orography. Okay, so let's look at the Indian monsoon for a second. This is a region to your paleoclimate. Oh, this didn't come out too good. This is a picture of the near surface moist static energy. So roughly speaking, if you get a high enough moist static energy off the equator, you're going to get rainfall pulled off the equator into this region. And I don't know if you can see this, but the maximum here is in the Bay of Bengal. And it's actually really low over India. Even though it's much hotter over India than it is over the Bay of Bengal, it's dry, so you have very little energy, because there's a lot of energy associated with that vapor if you can condense it. And then here's June, where the monsoon onsets, basically, that it starts raining like crazy in northern India, and the maximum is right here in the Bay of Bengal. Yeah, I don't know if you can see it, but this is the maximum moist static energy. It's not here, it's still here. Okay. And then as you get into July, and more, what happens here then, basically, as rainfall is happening in this region, and there's a low pressure being built here, and it's kind of sweeping moisture up into this region, and there's a barrier here. And the rain and the moisture is just coming up along this barrier, and it's just being pushed, just being pushed to the west. It's not because the land is heating up, drawing, and staying in. This barrier just allows moisture to go westward over India, and it rains like crazy over India. And so the moist static energy here goes up because the surface is being moistened by the rainfall that's propagating across here. Okay, so that's what it looks like today. The maximum moist static energy and the rainfall maximum. Rainfall maximum across the Indian monsoon is not over India either. It's over this Bay of Bengal. That's where the heaviest rainfall is. Okay, so now let's take a look back in time. Here we are today, and this is the amount of insolation you get at 30 degrees north in the summertime northern hemisphere. And you were kind of at a low today compared to kind of the last 250,000 years. And what we did is we want to say, how how was the climate different when you had much more insolation in the northern hemisphere summer compared to the time where you had really low insolation? So we're just gonna do a simulation of these two time periods where the only thing we're gonna change is the rotation rate of the sun. The greenhouse gases are gonna stay the same, continents are gonna stay the same, orography is gonna stay the same. The only thing is changing is we're gonna change the strength of the sun. And we did this with two different GCMs. I'm going to show you the results using the ECM 4.6 model. The reason why we use this one is because it's got isotopes in it. And we were trying to compare, we actually know what the isotopic composition changes here in time, and they're really big. And we know this from the stalagmites that come from caves. And the stalagmites are really precisely dated, so you can actually go back here. Now I think the error is 10 years out of 500,000 years, which is really incredible, right?
How long back in the past?
They go back now, 600,000 years is a typical time period, right? So they're really, you got lots of these cycles, and you can see them, and they're huge changes in the isotopic composition of precipitation compared to what we see in the modern climate. Okay. So we do these two core experiments, one with really high northern hemisphere insolation, strong insolation, and one with really weak. And everything else is going to be the same. And if you look at the difference at the top of the atmosphere, insolation coming down in these two time periods, this is January, June, December, and this is South Pole, Equator, North Pole. You can see the biggest difference is that there's large differences in the amount of insolation you're receiving here in June, July, August, basically. And these differences are close to 80 watts per meter squared. So these are really massive differences. A double CO2 forcing is 4 watts per meter squared. So these are 20 times more than increasing CO2. Okay, so you see really big differences in insolation in the summertime and in the fall here, where there's actually less insolation in the fall. Okay. And this goes all the way to the equator. So even here on the equator here, there's more insolation in northern hemisphere summer. Okay. And if you look at the difference between the low value, 207, and today, you don't see very much differences. So the reason why I bring that up is when I show you the differences here between high and low, you can think of it as difference between high times of insolation and today, because the difference between low and today is really small. Okay? So just think of these differences as how the climate was different at a time where you had lots of insolation in the northern hemisphere summer compared to today. Okay. So the last time we had that was 8,000 years ago. So it's early Holocene. Okay. So not surprising, the simulated northern hemisphere climate in the low forcing is similar to the modern climate. Okay. So here's the change in precipitation you see in the 850 hectopascal winds when you have lots of insolation in northern hemisphere summer compared to today, or the low times. These colors here, green, are a 50% reduction in rainfall here all through this region, Southeast Asia. And this, of course, it doesn't rain here today, and this is now a meter per season, right? So this is a lot of rainfall. This is basically moving the Indian monsoon to northern Africa, Pakistan, places where it's basically bone dry today. There are other changes on here that are pretty dramatic. The Atlantic ITCZ has disappeared. Actually, if you can see I don't know if you can see the wind. These are the wind changes. These wind changes on the order of 10 meters per second this way. So basically the trades have completely collapsed. And instead of having trades blowing from east to west across the Atlantic, they're blowing from west to east into Africa. So the source of this moisture here is as much, you can see these arrows, the source of the moisture is actually coming from the Atlantic, not from the Indian Ocean. This is a really profound change in how the tropics works. Okay, and this is a time of really the largest insolation we have in the last 250,000 years, but it is not too dissimilar to what we had 8,000 years ago. And of course, 8,000 years ago, the Sahara was green, right? And this region here, which is where agriculture starts, right, was also pretty green. It's not a place where you start agriculture today. It's really dry, but maybe not a surprise that agriculture started at this point because you had the right varieties and it was actually pretty moist environment. Okay, so the neat thing about this is that this model actually produces isotopic composition of rainfall, and you can go to places where there's caves, and you can drill in through a stalagmite, and then go back in time, and you know exactly where you are in time, and you can measure the delta O18, the isotopic composition of what's actually forming, what's condensing into forming stalagmites. And that's directly related to the delta, the isotopic composition of precipitation. So I can compare directly the model precipitation isotopes to what's actually observed in the caves. Okay, and there's no biology that gets in the way of this, it's great. So I just want to point out that these changes, you don't have to worry about the units. The model is what's colored here. The model gives you -7 here, and these numbers here are actually what the stalagmites give you. So -7, -4, -4. And the model's giving you basically those numbers here. Blue is -4, purple is -7. Right? And you see, the other thing that's interesting about this is throughout this whole region, you get the same sign of anomalies. And these anomalies in these isotopes are massive when we compare it to what we've seen across the Holocene. Right? And they're seen in the cave, so it's really beautiful. And we can actually then tell, because we have a climate model, we can say, why did the isotopes change the way they did? So in this region here, it's because the rainfall right down here, the monsoon was much more intense over India, actually, and I'll show you that in a second. And so the vapor that was coming up here was depleted in isotopes, and that's why this gets so negative. It's not so much that it's raining more here, it is raining more here, but not that much more. And of course here, it's a combination of it doesn't rain here today at all, and the vapor that is coming in to fuel this rainfall here is coming in from a long way away, and so that the isotopes have all been depleted already from the rainfall. Okay, so this is really nice because it's a really strong check on the climate model, and the climate model agrees with what the speleothems are telling you, so you can sort of believe the precipitation distribution. If you look at the top of the atmosphere radiation, and this is a picture of today, everywhere where it's white, actually the atmosphere is losing, the planet is losing more energy to space than it's gaining. So even though we're in the northern hemisphere summer and the sun is really intense, in these white places here, it's so clear and it's so dry basically that you're radiating from the surface right to space, and you're actually losing in the net, you're losing energy. That happens today, it happens in this low insolation case. If you go to the high insulation case, you can see now you're gaining a ton of energy. So you've actually completely replumbed the monsoon. Right? You've completely changed it from being a place where the energy is being lost today to a place where energy is being gained. Okay.
India is not there, right?
No, India's off the map over here.
Yeah, okay.
Yeah,
Okay.
so I'll show you
This is
this.
center in the Arabic Sea, something like that.
Yeah, this is the Arabian Sea. Here's
Okay.
the Arabian Peninsula. Here's the Horn of Africa. This is the Mediterranean
Oh,
Ocean.
I see.
Yeah, sorry about that. Yeah, yeah, it's kind of hard to see, isn't it? Yeah, yeah, yeah. This is, I guess, the Caspian Sea, the Black Sea, Mediterranean, Northern Africa. Okay. So with sufficiently high summer insolation, there's a fundamental transition to an entirely different state. Instead of actually having rising motion and convection in the Bay of Bengal, and in this region here, you're having sinking motion, and the energy is spewing energy to space. Today, in times of high insolation, you've shifted the rainfall and the convection to being over this whole region, and it's a place where energy is being gained in the climate system. Okay. Maybe I'll skip this, but we actually know why the Eastern Mediterranean is kind of a desert today, and it has to do with the fact that you have convection in the Bay of Bengal. This is, I think maybe I'll skip. What time is it?
It's 11:05.
Okay, I'm gonna skip this. It's just, it's a detail. But today, let me see. I'll just show you a picture. Today, if you put a heating, like due to rainfall, latent heat release in this region here, you get sinking through this whole region here. This is an idealized model. This is what the observations say. You have upward motion here, and you have downward motion all through here, and then upward motion here. So this sinking here, we know today is mainly due to the fact that you have convection in the Bay of Bengal. If you shift this convection down over here, then you lose the dynamics that causes this sinking, and you can spread the monsoon to the west. Okay, so how do you break this? If you look at just the seasonal cycle of the insolation at 30 degrees north in these two cases, here's like today, it goes up here, this is June, that's the maximum insolation, and it comes down here, here's December, and then it comes up again, June, December. If you look at times of high insolation, it's not so much, yes, the insolation is greater in the summertime, but what's important here is this thing comes up really fast, and it keeps on going up fast. So if I think about heating an ocean in a land, I can basically just say in this case, the land's going to respond instantly to a heating. The ocean's going to say, I have to integrate this thing up, I have a big heat capacity, it's going to take me a few months to get my act together. So if I just bring the insulation up quickly up to a really high value, the land is going to heat up really quickly. The ocean's going to say, yeah, I'm going to heat up some more, but it's going to take me a few months. So that initially, like in June, there's going to be a much bigger difference between the temperature of the land and the ocean, right? And if I can make that temperature difference big enough, today it's only 12 degrees. If I can make it big enough, I can actually make it so the moist static energy is highest over land, and therefore the convection is going to happen there, and the convection will shift from the Bay of Bengal to the land. Does that make sense to everyone? As I said, if I heat the land up enough, I can make the moist static energy highest over land, and that's where it's going to rain. Okay. Yep.
This hypothesis will also work over the Eastern Mediterranean Sea. So
it will. Yep.
How is it possible to separate the impacts of the ocean, large-scale ocean, land temperature contrasting compared to Eastern Mediterranean and the local scale?
So even today, even like in the Arabian Peninsula, even though it's really hot, the moist static energy is not as high as it is over the ocean. So I somehow have to make it hotter. And the way I can make it hotter is just to make the sun go to much more high value in summer, and the land temperature is going to immediately scale with this, right? If I have 20% more insulation, I'm going to have 20% higher temperature. The temperature change from winter to summer is going to be 20% more over land. But over the ocean, it'll be 20% more, but it's going to be lagged by several months. So that difference is going to be greater. Right? The difference in June is going to be greater, because it's still going to take the ocean a couple months to catch up. And so what happens is I can make the land temperature really go skyrocket. And so instead of 44 degrees, it's going to be 50 degrees over India. And therefore, then when I calculate the moist static energy, it will be higher over land. Right? Okay, so here's the picture of it. I don't know if you can see it. This is the time of low insolation. Like today, the maximum moist static energy is right here in the Bay of Bengal. Okay, and then if you look at so the convection centered over the maximum year moist static energy. Okay. Here's what happens in times of high insolation. The moist static energy maximum is now all the way across northern India, all the way into this region. So it's really shifted. The difference plot is shown here. So there's a huge change in where the moist static energy maximum is, from being Bay of Bengal to being all across this region here, which is why it rains there. Okay. So convection here is centered over land in the high insolation. And you can think of this as a classic textbook monsoon. Land heats up, draws the air in. Okay, that doesn't happen today in India, but it probably did happen at times of really high insolation, like the early Holocene. It probably is true. The land heated up enough to draw the moist air in and to give you convection. Okay, so there's one more monsoon which I talked about briefly, the Mayu, which is not a monsoon at all. And that's being written up right now by John Chang and other people, including myself, or it's in review. Okay, so 3 types of monsoons. With strong enough asymmetric hemispheric heating, so when the northern hemisphere heating, say, is big enough compared to the southern hemisphere's heating, you can pull the convection away from the equator into the, say, subtropics at 20 degrees. And that is mainly described today by an ocean-atmosphere interaction, not a land interaction. So Indian monsoon is a good example of that. Or if all you have is land and you've lost all your ocean because you've paved it all over, then you just get the classic land atmosphere monsoon. The thermodynamics, that is the maximum moist static energy, is really important for that. With only modest asymmetric heating, if you can't if you can't get the off-equatorial moist static energy so large to really pull things away from the equator, then all you're going to get is an ITCZ. All you're going to get is these things that move slightly away from the equator, and they try to follow the sun, lag by a couple months because the ocean is integrating this stuff up and maximizes a few months after the maximum insolation. And these features are due to flow instabilities that shed waves, for example, in the Atlantic, in the Far Eastern Pacific, or they're due to convection that's organized by mixed gravity waves. That's the answer in most of the Pacific. And actually, probably even in the Indian Ocean in southern hemisphere summer. I haven't studied those features, but I bet you those things at 7 degrees south in the Indian Ocean are basically just easterly waves that are propagating from east to west. And in those cases, the thermodynamics is important, and so is the dynamics really important. Okay, and I think that's it.
Thank you. Thank you, David. Very illustrative.